Okay. Well, it looks like the first video went down, and I'm going to wait for other folks to join up on this one, and then we'll get restarted. We'll get restarted here in about 2 or 3 minutes and give other people a chance to get back on. Otherwise, this will be available on YouTube for later. Okay. Looks like not everybody has been able to migrate over to this, but this will be available on YouTube later, so you guys can catch up here. I'm also going to upload to another site a video that I'm recording here locally. So one way or another, we will get all this information on the internet. The area where people mentioned that the video cut off was way back here. Explaining the difference between fork and clone. The big difference with clone is this is really used for finer grained process creation and for thread creation. And then Windows has got a different approach. It doesn't use a fork-like call like Linux does. It uses a create process and create thread call, which is a little bit different. And make sure I am screen sharing. Oops. Let's see here. There we go. Okay, sorry about that. I don't really feel strongly that there's a particular advantage or disadvantage to this approach. So the causes for process termination, two common cases are the normal exit or return from main, an error exit from the program that's really a part of the program logic to exit, and types of fatal errors, so different types of crashes that the program will have. And usually these are violating rules for the memory, trying to execute instructions that are protected by the operating system, or having faults with particular instructions like dividing by 0. Let's see if anybody else is getting on here. Okay. So we went over the different types of files in Linux. Regular files are just files that hold data. Folders are collections of files and other folders. Symbolic links are types of files that basically point to other files. So we can look at the lib folder, and we can see an example right here where a symbolic link points to a different file here. Other than that, the other two types of files that are available are block device files and character device files, and these are located under the dev folder. And a good example of this would be this file right here, mouse 0. So this is a file on the file system that basically is the way that a program can access the mouse. Let's see here. Over these. And we'll get into these other file types here when we get into inter-process communication. It'll be more appropriate to talk about that then. So file system, system calls. A majority of the system calls that are available in a lot of modern operating systems are file system calls. So a few of these calls would be open, which opens or creates a file. Create, interestingly, not with any, creates new files. Close closes a file. Else seek will update the file descriptor to a different offset within the file. This is used for random I/O. Read and write are fairly self-explanatory, to just basically read from and write to a file. And dupe and dupe2 are used for file redirection. So a good example here would be like this. If I say echo hello, it'll print to the console. But if I do that, right here, the way the console does this is through the dupe2 call. And we can see that the data went to the file. So what this does is it redirects the output from the console to a file. And the system call that does that is dupe2. These other ones, these two right here aren't used as often. They're used for setting advanced I/O properties and for working with device files. These here are basically to check security and file metadata. And these two right here are to update file ownership and file permissions. And there are just lots and lots of file system calls working with each of the types of files. And let's take a closer look at opening and writing a file. The open function here accepts a path, flags, and a mode. Flags describe how the file is opened. Is it open to be appended to? Is it going to be truncated? Are we doing asynchronous I/O? Are we creating a new file if it doesn't exist? Mode is basically the permissions with which we're going to open or create the file. Return from this, from the OS, is an integer that acts as a pointer to the file. The close function takes that handle again, and will close the file for you. Writing to a file, the write system call will take the file descriptor, a memory buffer, and the size of that buffer. And you get a return code. Basically, if you ask 1,000 bytes to be written, there isn't really a guarantee in the write system call that all 1,000 will be written. This is most common in network file systems or networked I/O. So you may have to call write in a loop. An example of that here is a write that handles incomplete writing. What happens here is a file is created. We're writing a string foobar to that file, and we're handling the fact that writing to that file may not be complete. So that's what this algorithm here does. Reading from a file is basically the same case. It will return -1 if some error occurred, 0 if you've reached the end of the file, and the number of bytes written otherwise. So this is a reading from a file, writing to the console algorithm. While we have a buffer, and we sequentially read from the file in a while loop, and we write the data back out to the console. And yeah, vaguely this is similar to the cat command that we use right here to print out this file. Seeking within a file, not all files support seeking, but this is basically how we do random access I/O. The use of the seek calls has performance implications. We'll get onto that a little bit later in this lecture. Let's see here. Standard file descriptors. Every program in Linux is given a standard input, standard output, and standard error. Standard input is where the console accepts keyboard input, or if something is being redirected to the program, it comes through here. Standard output by default goes to the console, but it can be piped out to another file like we saw earlier. We mentioned this. And I want to end this lecture on point of performance. And really this story is really the case for a lot of for a lot of system calls and operating systems. So if we do fine-grained I/O operations, and I'm going to reinforce this on Monday's lecture, there's a lot of overhead. You have a long process that's involved in terms of making a call into the operating system, and that's a lot of overhead to pay. So we can see in this example right here that writing with a small buffer size a lot of times doesn't get very good I/O performance. But if we write fewer times with larger buffers, we can get much, much better I/O performance. And this is really a real good example of the idea of context switch overhead. I'm going to stop right here, and I'm going to dig into this a little bit more on Monday. For those of you able to view the video right now, I know that it cut out about an hour and a half in, and sorry about that. I blame Google. But I have a locally recorded version that I will also be posting online that will have everything. And my hope is that this will cover the bit of it that was lost and will also be available on YouTube. So enjoy the rest of your evening, and I will definitely see you on Monday in class. And I will announce the first homework assignment then. So be sure to attend. I'll that evening be sure to post on Piazza the details of the homework assignment. Well, thank you for your time and for your understanding and patience with me in not having the class available in the classroom on Monday because of the issues with the building, and I hope that having this online is a way to keep in touch and keep the class moving. Feel free to email me any questions you may have, and I will see you guys on Monday. Have a great evening.